Hey, this is Jack Jackson back again. We're working with matrices and transformations. And remember, if you watched the last video and had a TI Inspire calculator, CAS calculator with you, and programmed it along with me, um, then you now have functions available in your Inspire CAS for producing transformation matrices of all of the five types of isometries: identity, transformation, translation, rotation, reflections, and glide reflections. And we can access them by typing in their names, if you remember, like ROT for rotation. Um, or you can get them by pressing the variables key, the VAR key, and you'll get a drop down list of those things that you have programmed in, those functions and other variables, things that are programmed in. Just select it from the list and then type in the parameters. You do need to remember what order what inputs are needed and what order. One thing that might be useful to do with that is to actually create a little document within your Inspire. Well, create a text window inside your document and type in what the inputs are, or just make yourself a little index card, little cheat sheet to remember the order. Okay, so let's move on now and talk about inverses of isometries with matrices. We know that transformation matrices all have inverses, but just as transformations have inverses. Actually, all matrices with non-zero determinants have multiplicative inverses. The following table summarizes the inverses of isometries in transformation form and in the 3 by 3 matrix form. So on the left in the blue, first two columns, we have the original transformation, which its description as a transformation and the matrix for it. And then in red on the right, we have what the inverse transformation is, its description as a transformation and the matrix for that. Well, the identity is its own inverse. So easy enough there. And it is this matrix with ones down the diagonal, zero everywhere else. A translation by HK we saw could be the identity matrix, except you replace these first two things in the last column by your vector HK. The translation will be a translation by the vector minus H minus K, so it will be this matrix right here. A reflection about a non-vertical line, y equals m plus b, we found had this somewhat complicated matrix here. Well, it's going to be its own inverse. A reflection about any line is its own inverse, so same matrix there. Same for about a vertical line. We found this matrix worked, and then the same inverse. Rotating through the origin by an angle of theta gives you this matrix. Its inverse is a rotation through the origin by the angle minus theta. So just take all the thetas here and put in minus theta, and you get this matrix. You may look at that and say, well, that doesn't look like that. Well, it's because we simplified it a little bit. Cosine of minus theta is cosine theta. Sine of minus theta is the opposite of sine theta, so that cancels that minus to a plus, but it can be moved the minus here out front, and the cosine just absorbs the minus there because it's an even function. Cosine's even, sine is odd, so that those even and odd identities allow us to simplify that. So that's what that turns out to be. Now this one's a little more complicated. Rotation about the point HK through the angle theta turned out to have this form. Its inverse is a rotation through the point through an angle minus theta. So again, we replace all the thetas by minus theta and simplify, and we can get this. A glide reflection about the mirror line y equals mx plus b and the parallel vector hk, note that k over h is the slope m, was this vector. And a glide reflection, its inverse is a glide reflection about the same mirror line but by the opposite vector. So take this and just replace, let's see, same mirror line. Okay, so that's not going to change, but you're going to replace k and h by opposite of k and opposite h. So here when you square these, that stays the same. So a lot of these terms are going to be the same. Here the two minuses multiply and doesn't change. Here we have the two minuses multiply. That doesn't change. Let's see, but then the h does change, the opposite sign. So there it is, and so forth. So you just flip the signs on both h and k. A glide reflection about a vertical mirror line x equals h, and parallel vector 0k we found was this matrix, and its inverse will be a glide reflection about the same vertical mirror line, x equals h, and an opposite vector 0 minus k, so just replace k by minus k there, and you get that one. So notice we can obtain these inverse matrices in two different ways. Just by taking this matrix and doing these substitutions like I just did, or we can use the calculator to do the same thing. So for example, to find this matrix for the rotation here, we know that ROTO theta is a rotation about the origin of angle theta, which would give you this matrix. But if you do ROTO minus theta, that simplifies to this matrix, which is what I have right there, and the calculator will do it for us. Again, notice it's been simplified using the even and odd trigonometric identities. But there's actually an even easier way to find these inverses. The TI Inspire knows how to find, built-in, knows how to find the inverse of any square matrix with a non-zero determinant. We simply raise the original matrix to the power -1 on the TI Inspire to get the inverse matrix. And since we have shorthands for entering these matrices without typing all this stuff again, we did that already, programmed it in, we can do this, ROTO of theta to the power -1, and you're going to get this same matrix here again. So for example, to get this glide reflection thing directly, we can do this. We can do GF of HKB, which is this, but then raised to the -1 power will be the inverse matrix, and it gives us this. Okay, and this may or may not look exactly like this up here when you get it out of the calculator, but we do have to, most of them are exactly the same, but there are a couple of them that we need to check. Let's see, the 1, 3, and 2, 3 entries. So 1, 3, and 2, 3, these two right here. These don't look exactly like these here. Well, notice these are not with a common denominator. Okay, perhaps I should have put them that way, but they're not. So what I can do here is to take those expressions right there, each one of them, get a common denominator and tell it to factor it. It looks like that, and this one looks like this, and that is exactly what we got here out of the calculator. So yeah, they're equivalent. We could either, if you want, you can, instead of having this one right here, you could write it like this. In fact, we could go and just factor these things down and do that instead. If we'd rather, it doesn't matter. So finally, what do we have? We have all the inverses. We see what the inverses of each one are, both as a transformation and as a transformation matrix.